Welcome back. This lecture will be on higher order linear equations. So remember what a first order linear equation is. It's dy dt plus a of t times y is equal to f of t. And we're going to generalize that now to allow higher order derivatives. So instead of starting with the first derivative of y, we're going to start with the nth derivative of y, dn of y dt to the n. And then you're allowed to have a function times the next derivative. So that's a1 of t times the n minus first derivative. And all of the lower derivatives, n minus 2 and so on, all the way down to you're allowed to have some function times dy dt. And then finally, final function an of t times y is equal to f of t. And I forgot to write the times y there just before the equal sign. So notice that you have all of these derivatives of y, from the nth derivative down to the first derivative, and y itself. And you have these functions of t as coefficients. And on the right-hand side, you have this non-homogeneous term. Just like in the linear case, you have some function on the right-hand side. So this is the general form of a nth order linear differential equation. And let's talk about the solutions. It's very similar to what happened in the linear case. Let's suppose you're looking at some interval from TL to TR, which might well be minus infinity to infinity, and you're looking for some function y of t, which satisfies the equation for all t in this interval. That's clearly, that's just the notion of having a solution. And, well, to say that it satisfies this, of course, means that all of the derivatives of y are defined. That is to say, the nth derivative and the n minus first derivative and so on, the first through nth derivatives all have to be defined. So that's kind of goes without saying when you're talking about solutions of these things, that your functions are n times differentiable. And so, for example, suppose I gave you a very simple differential equation. The second derivative of y is equal to 0. Well, that's valid for t between minus infinity and it's defined for t anything. And what's the solution? Well, the constant is allowed, but it could also have a function of t, a linear function of t, d times t. And that's it. All of the, we know from calculus that if the second derivative of a function is 0, then it's a linear function of the form c plus dt. And that's the arbitrary, that's the general solution. And notice there are two arbitrary constants, c and d. And that's a general feature of these things. So let's look at another example. Suppose I looked at the fourth derivative of y was equal to 0. Well, y would be c0 plus c1t plus c2t squared plus c3t cubed. It's a fourth order equation, and there are 4 arbitrary constants. And that's no accident. So let's look at an initial value problem. Let's say you have an equation, the nth derivative of y plus dot 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 down to the first derivative plus some function times y. I forgot my y again. Some function times y is equal to f of t. Then and then what's an initial value? How do you specify the initial values? Well, it's an nth order equation, so you must need n initial values. So let's specify that the value of the function at ti is given as, say, y0. That's a single condition, but as we saw, we need more. So let's specify the first derivative at the initial point, call that, and say that's t1, and the second derivative, and let's ask that that be equal to some y2, and so on, all the way up to the n minus first derivative. Let's specify that. So that's n initial values, y 0 through yn minus 1. You can specify those arbitrarily. That gives you n conditions that you need to satisfy, and that's exactly the right number of constraints that you need in order to specify the constants. So just like in a linear equation, you need one equation to specify the constant. In an nth order equation, you need n initial values. Okay, so let's do a simple example of that. Let's take the equation, the third derivative of y is equal to 0. And let's make up some initial conditions. Let's say that y of 0 is 1, and y prime of 0 is 2, and y double prime of 0 is, let's say, minus 4. It's a third order equation. That's 3 initial conditions. Well, we know that y is c0 plus c1t plus c2t squared. That's the general solution. And there are 3 unknowns, c0, c1, and c2, and we should be able to determine them. I'm going to call this capital Y. And so let's see, y of 0 is c0, and y prime of 0 is, let's see, take the derivative, that's c1. And y double prime of 0 is, when you take the second derivative, you get 2c2. And you set those equal to the desired 1, 3, and minus 4, and conclude that the unique solution with the given initial values is, well, let's see, c0 has to equal 1, c1 has to equal 3, and 2c2 has to equal minus 4. So that is to say c0 is equal to 1 plus 3t, and then c2 is equal to minus 2. So this solution with the given initial values is 1 plus 3t minus 2t squared. Okay, you all knows what comes next. Here comes the existence and uniqueness theorem. So anytime you're given a class of differential equations, you get some sort of theorem about existence and uniqueness of solutions. And linear equations are the nicest, so the theorems are particularly simple and strong. So let's say we're given functions a1t through an of t and f of t, and let's say they're continuous on some interval from TL to TR. That's the basic setup. Then we can consider the differential equation with these coefficients. And the initial value problem is that you're given some t initial in this region. And the statement is that for any initial conditions, y0 up to yn minus 1, there exists a solution to the equation, and it's unique. There's a unique solution of the equation with the given initial conditions. That is to say, y of ti is y0 and y prime of ti is y1, and so on. Here are the initial conditions written out. And so that's the usual thing. There exists a unique solution sort of locally at the given point. And since it's a linear equation, it's actually really nice. You're actually guaranteed that this solution y of t is a perfectly nice function on the entire interval. it has at least n continuous derivatives for all t in this interval from TL to TR. So remember back in first order equations, for linear equations, this kind of thing happened, but the general situation is not nearly as simple. But higher order linear equations are like linear ones in that regard. So let's look at an example. Suppose I gave you this equation. It's a second order equation. And what can you say about existence and uniqueness of solutions? Well, let's see. These coefficient functions are nice, except that t equals 1 and t equals 3. So as long as you throw out those points, everything should be fine. So draw the t-axis and specify the points 1 and 3. And you see that in the region from minus infinity to 1, everything's hunky-dory. So if you gave an initial value in this region, it would extend to the entire region. If I gave you an initial value in this region, it would only be good from 1 to 3. And if I gave you an initial value to the right of 3, it would be good from 3 to infinity. So in other words, the solutions are valid in as large a region as they possibly can be. So here it's written out. The interval of validity of your solution is either minus infinity 1 or 1, 3 or 3, infinity. Let's do another example like that. Suppose I gave you the equation t dy, the second order equation, t d squared y dt squared plus dy dt plus y is, let's say, e to the t. Well, all of these equations look, all the AIs are fine, right? So this should be defined everywhere. Is that right? Minus infinity to infinity? Sure looks like it, but. No. The problem is this t out front. It's not in normal form. The coefficient of the top term is required to be 1, so you have to divide by t to put this in the correct form, and you get a 1 over t dy dt and so on for the other terms. So that tells you that the point t equals 0 is bad. And so the correct answer is that the interval where the solutions are defined will either be minus infinity 0 or 0 to infinity. Okay, let's go on and talk about homogeneous equations. So just like in the linear case, there's two cases, homogeneous and non-homogeneous, for first order linear equations. So for higher order linear, there's a similar dichotomy. So here's your general nth order equation. Looks like this. And at the end you have this an of t times y, and that's equal to f of t. That's the general nth order linear equation. And to say that it's homogeneous is to say that f is just 0. So that's the case we're going to be talking about, where the right-hand side is 0. And there's a key idea here that there's a notion of linear differential operator. And that's what this is about. So before I say what that is, let me just give a little digression here. Let's remind ourselves what a linear function is. Never mind differential operators for the moment. Let's just talk about linear functions. If you take the function f of x is equal to k times x, that's a, so to speak, linear function. Its graph is a line, after all. And what does it mean? Well, f of x plus y is f of x plus f of y. Right? Why is that? Well, because on the left-hand side, f of x plus y is k times x plus y. And on the right-hand side is kx plus ky. And those two things are indeed equal. That wouldn't be the case if you had x squared, say, but since it's just the first order in y, it's true. And similarly, f of c times x is c times f of x. You can pull constants out of linear functions because the left-hand side is k times cx, and the right-hand side is c times kx. And those two things are indeed equal. And if you had more than one variable, so for example, suppose I gave you a function of two variables, x and y, the function cx plus dy is a linear function. Excuse me. So that's just to remind you about functions. Let's go back to differential equations and do something analogous. So we're talking about this equation, and we're going to define an operator, or a differential operator called L of t. And the definition is it's the operator taking the nth order derivative plus multiplying by a function and taking the n minus 1th derivative, and so on. I'm not writing in the y, I'm just writing these differential operators, the various derivatives. And there's d by dt, and then at the very end there's an an of t. So just, I'm taking the left-hand side of this equation and just throwing away y. And this is an operator, L of t. What does that mean? This is something that you can apply to a function. If you had this operator, L of t, you can plug in any function and get a new function by evaluating the various derivatives at the function and multiplying by the various ai of t's and adding them up. That gives you a new function. So L of t is a map from functions to functions. So let's look at an example. Let's say L of t was, let's say, t squared times the first derivative plus sine of t. So that's an operator. What does that mean? If you apply it to a function, f, you get a new function. You get a new function, t squared times the derivative of f plus sine of t times f. So it takes one function to another. And I'm just saying that you're just plugging in these f's. The operator doesn't have the f's in it, and you're just plugging in f here for the derivative, and you're here when you're multiplying it times just the function sine of t. So, for example, what does it do to the function t cubed? Well, it says multiply it by t squared, and then take the derivative, and then add sine t times the function itself. So it takes the function t cubed to this function 3t to the 4th plus t cubed sine of t. As another example, this operator L of t takes the function t to what? T squared times the derivative of t, which is 1, plus sine of t times t. That's a misprint. That should be a t. Sorry. And let's look at L of t applied to t cubed plus t. That's applying it to the function. Well, it's t squared times the derivative of t cubed plus t plus sine of t times t cubed plus t. And if you work that out, it's what? It's t squared times, let's see, 3t squared plus 1 plus sine of t times t cubed plus t. And notice that I've got t squared times 3t squared here. Just like up here, I have t squared times 3t squared when I applied it just to t cubed. And I also get sine of t times t cubed. And the other terms are, I get t squared times 1. And I also get sine of t times t. As I said, this 1 here should have been a t. So it's all the same terms, just in a different order. So if I change the order, I can write this as t squared times 3t squared. I'm just taking the red terms now, plus sine of t times t cubed. That's the red terms. And the blue terms are t squared times 1 plus sine of t times t. And notice that the thing underlined in red is L of t applied to t cubed. And the thing in blue is L of t applied to t. So what do I conclude? That this operator, L of t, applied to the function t cubed plus t, is just the same thing as L of t applied to t cubed plus L of t applied to t. So this says that L of t is a linear operator. And that's the punchline. L of t applied to a sum of functions is the sum. You can apply them to the functions one at a time. So here's the theorem. Suppose you have a differential operator of the form the nth derivative plus a function times the nth minus 1th derivative, and so on, plus dot 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 down to a function times the first derivative plus a function. That's an operator. Takes functions to functions. And the statement is that it's a linear operator. And what that means, just to reiterate, is that if you apply this operator to f plus g, it's the same as applying it to LT of f, applying it to f and then applying it to g. And secondly, if you apply it to a scalar multiple times a function, you can pull the scalar multiple out. That is, by definition, those properties define what it means for an operator to be linear. And this has a very important consequence for equations, which is the following. Here's my homogeneous equation that I've been talking about. And I'm just rewriting this as saying it's exactly the same thing as you take this differential operator L of t by pulling out these coefficients. And the differential equation is just, can be written in shorthand now as just saying that L of t applied to y is equal to 0. That's just a nice shorthand for this equation. Well, it's more than just a shorthand. It tells us that, notice that if L of t of y1 is equal to 0, and L of t of y2 is equal to 0, then by the linearity property, we know that L of t times y1 plus y2 is equal to 0. Because by linearity, this is equal to L of t y1 plus L of t y2, which is 0 plus 0. Okay, so here's the conclusion. suppose I have two solutions of my equation, y1 and y2, then, well, I just saw that LT applied to y1 plus y2 is 0, but you can also throw in constants linear by linearity, and you conclude that L of t times c applied to c times y1 plus d times y2 is equal to 0 for any c and d. And this is called the linear superposition theorem, or linear superposition principle. It says the following. Suppose I have a homogeneous higher order linear equation, and suppose I have a bunch of solutions to it, y1 through ym. So here's my general nth order linear equation. If you give me a bunch of solutions, then you get a whole new bunch of solutions by taking c1 y1 plus dot 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 cm ym for any constants c1 through cm. So that's the linear superposition principle. If you have a bunch of solutions, you can add them, you can multiply them by constants and add them and get new solutions. And that's for any constants. This thing in the red box is we just refer to as a linear combination of the y's. So this is very powerful. It tells you exactly what the solutions of a homogeneous higher order linear equation look like. They're built up out of solutions using the superposition principle. All right, that's a good place to stop. See you in class next time.